Hello again, welcome back. Today we'll be doing section 7.2, volume, specifically the disk method. So if we think back to our two-dimensional geometry days, just a plain circle, the area of that circle was just pi times r squared. Then as you got a little farther in your geometry class, you got to the right circular cylinder, aka a soup can. And for that, when you wanted the volume, you took the area of the top and just multiplied it by the height. What we're doing today kind of resembles the soup can just turned on its side. So the idea is we're in here in the XY plane somewhere. We have some type of figure, and we're going to revolve it about the x-axis later on, the y-axis and other axes. If we make one little shell here, this would be delta x in width, and we'll call this r of x in height. And we swing these around and make a soup can out of it, a right circular cylinder out of it. The change in volume is pi times our radius squared times our height. Our height is delta x since we turn the soup can sideways. As we let delta x go to 0, or the number of subintervals I go to infinity, we get the volume is, you can pull the constant pi integral from a to b of r of x squared times dx. And we would get a similar idea if we revolved about the y-axis, just switching our x's and y's. So we're making solid shapes by spinning them about an axis. So we'll start with just a fairly straightforward one. We're going to revolve y equals x squared, so a basic parabola about the x-axis on 0, 3. So 0 squared is 0, 1 squared is 1, 2 squared is 4, 3 squared is 9. So here's a quick rough sketch of the solid that we're forming. We're spinning this again around our x-axis. So our volume, pi times the integral from, we're going left bound 0 to right bound 3. Don't forget it's r squared, not just r, so x squared squared. Here is our radius. Here is the fact that we happen to be squaring it, and our width is delta x. So volume, pi integral 0 to 3 of x to the 4th dx, which would then be pi over 5 x to the 5th evaluated from 0 to 3. So that's pi over 5 times 243 minus 0. So our volume is 243 pi over 5 cubic units. So notice we're in 3 dimensions, so it's not square units anymore. It is cubic units since we're talking volume. So this next one, we'll switch it up, and this time we'll revolve about the y-axis. The rest of it will keep the same. So as far as our 2D graph, the initial shape looks the same, only now we're spinning it about the y-axis. So a different solid shape. So in other words, think of it sort of like a horizontal rectangle as opposed to the vertical ones. So our volume, pi is still involved since we're talking circles. But this time, our x is from 0 to 3. That makes our y from 0 to 9. 0 squared and 3 squared respectively. Our original formula, y is x squared. If we solve that for x, x is the square root of y. Usually we would have the plus or minus. We'll just take the plus in this case. So our radius, square root of y squared. So volume is pi r squared times the height. Our height this time, dy. So volume, pi integral 0 to 9 y dy, which is pi over 2 y squared, evaluated from 0 to 9. So our volume is 81 pi over 2 cubic units. Okay, so next up, we're going to revolve about a different axis, not around one of the basic axes. This time, we'll revolve about the line y equals 1. And here we're going to let x be in the closed interval 1, 3. So I like to kind of make a sketch first. So x is between 1 and 3, so 1 squared is 1, 2 squared 4, 3 squared 9. So that same curve we've been working with, just we don't go all the way out to the 0, 0. And we're revolving about the line y equals 1. I'll put that in as a dotted line here. So this is our solid. Instead of revolving about the x-axis, we're revolving about y equals 1. So our radius, in this case, would be the top function minus the bottom function. So then our volume is pi times the integral from 1 to 3 of our radius squared times volume, pi times the integral from 1 to 3 of x squared minus 1 squared. That would be x to the 4th minus 2x squared plus 1 times dx. Our volume, pi times x to the 5th over 5 minus 2/3 x cubed plus x, evaluated from 1 to 3. So in our volume, plugging in the 3, we end up at 168/5. Plugging in the 1, we end up at 8/15. And each of those was multiplied by pi, so 496 pi over 15 cubic units would be our volume. All right, one other application. The volume of a cone. I want that to be a closed interval. So how I'm picking out the equation of this line, let me make you a quick sketch of what's happening. So we're here in the xy plane. I'm going to start at the origin, and I want to end up making a cone with a radius of r and a height of h. Well, 0 to h would be h, which would make this height as r. So if we did the equation of that line, that's our line. Y is r over h times x. And we're going to rotate about the x-axis. So our volume, pi times the integral from, we're going from 0 to h is where we're interested in. Radius squared, r over h, x quantity squared, times the height of each soup can, be dx. So our volume, pi times the integral from 0 to h of r squared x squared over h squared times dx. So pi times r squared x cubed over 3h squared. So we're looking at r and h as being arbitrary non-zero constants, and do the antiderivative of the x squared is x squared over 3. X cubed over 3, my apologies. And we're evaluating from 0 to h. So our volume, hang on to that pi for a minute. We have r squared h cubed over 3h squared minus r squared 0 cubed over 3h squared. So our volume, pi times r squared, h cubed over h squared is h to the 1st, and we just have our 3 downstairs. Second term, 0 times anything is 0. And this is in cubic units, of course. So if you ever wondered from your geometry class where that 1/3 came from when you were doing the volume of a cone, that is where calculus is where that came about. So the next thing we look at is the idea of the washer method, which is really just sort of the disc method with a hole cut in it. You have a little thing of my wife's ribbon here. This is the idea with the washer method. Find the volume of the whole disc, and then find the volume of the section you'd like to slice out of it. Not terribly dissimilar to what we did when we found the area between two curves. So we'll call the radius big R and little r, respectively, for the outer and inner radii. So pi times the integral from a to b of big R of x squared minus little r of x squared times dx. So the idea is we have the big R center to the outside minus little r center to the inner radius, the part we want to cut off. So we're going to find the volume of the solid formed by revolving y equals root x, y equals 1, x equals 1, x equals 9, about the x-axis. So first, let's get a picture of what we're doing. Just a quick sketch. Does not have to be a masterpiece. So y equals square root of x, square root of 0 is 0, square root of 1 is 1, square root of 4 is 2, square root of 9 is 3. So we have our square root, a little bit more of a curve to it than what you see on my little unscaled hand sketch there. My apologies. Then we also have the line y equals 1. So this is the idea here. This is the solid part that we want, from x is 1 to x is 9. And we're going to spin it around the x-axis. In other words, there's a hole in the middle that we're going to need to slice out of this thing. So our volume, pi times the integral from x is 1 to x is 9. Outer radius, square root of x squared minus inner radius is 1, also squared, times dx. So volume of the whole thing minus drill out the hole. So our volume, pi times the integral from 1 to 9 of x minus 1 quantity times dx. So our volume, pi times x squared over 2 minus x, evaluated from 1 to 9. So this would be 64 halves pi 32 pi cubic units. All right, so one more washer method. So notice here they did not give us bounds. They just told us we're revolving these shapes about the x-axis. First, let's find out where they meet. So half x squared is 2x. So x squared is 4x. X squared minus 4x is 0. So x by x minus 4 equals 0. So x is 0 or x is 4. So now we figured out what the bounds were. We'll make a quick sketch here. So they, of course, both meet at 0. When x is worth 1, f is at a half, g is at 2. When x is worth 2, 2 squared is 4, half of 4 is 2, f is at 2, and g is at 4. So there's our linear, and there's our curve. So g is the top function, f is the bottom function on this guy. And we're swinging this around the x-axis again. So this is another washer scenario. We're going to take the whole volume and cut out what we don't want. So volume would be pi times the integral from, we figured out our bounds, 0 to 4. Outside radius is from function g. So outside radius squared, 2x quantity squared, minus inside radius is the curve function f, half x squared quantity squared times dx. So our volume, pi times the integral from 0 to 4, a little bit of simplifying inside, 4x squared minus x to the 4th over 4 times dx. So pi times 4/3 x cubed minus x to the 5th over 20, evaluated from 0 to 4. So our volume, 512/15 times pi cubic units. And in general, I mean, I'm going to want you to leave your answers in this form. I'm not really looking for a decimal approximation unless the problem specifically requires it. Now, we do occasionally have problems where we need a pair of integrals. So we're looking for the volume of the solid form by revolving the region bounded by, and we'll give you a curve and a few lines about the y-axis. So we're revolving region BDD, shortcut for bounded by, y is opposite of x squared plus 8, y equals 0, x equals 0, x equals 2, about the y-axis. So again, to get a rough idea of what's happening, make a sketch. So y is opposite of x squared plus 8. Vertex is at 0, 8. It's a parabola. It's opening down. We're looking between x is 0 and x is 2. So notice here, we're looking at a curve, but then once we hit 2, now we're looking at a line dropping straight down. So we have two distinct parts when we start spinning this around the y-axis. We have this solid rectangular base at the bottom, and then we have this parabola being spun at the top. So we have two different behaviors happening in this thing. So if x is worth 2, you can see that y is worth 4. So that would be this point here. We have, of course, 0, 4 here. We have 2, 0 there. I'm not sure where 0, 4 came from in my head there. And of course, our vertex here at 0, 8. So we have really two different shapes going on. We have the curve at the top underneath that parabola, and we have the soup can at the bottom. So our volume, both of those are going to involve pi. One of the integrals is going to be looking between 0 and 4. And it goes out as far as 2, radius of 2. Don't forget to square your radius, though, times dy. We're spinning this around the y-axis, so remember this is a horizontal rectangle case. So if y was opposite of x squared plus 8, then x squared is 8 minus y. X is equal to, usually would have the plus or minus. We only need one of them. We'll just arbitrarily take the plus. Square root of 8 minus y. So plus integral from 4 through 8 is our next set of behavior in this solid. We still have our pi with this whole thing. We just bracketed it all together. Radius this time, 8 minus y underneath the square root, and then we're going to square it and multiply by dy. So our volume, pi, times the quantity integral from 0 to 4 of 4 dy, plus integral from 4 to 8 of 8 minus y times dy. So our little puck at the bottom and our curve at the top. So our volume now, pi times 4y evaluated from 0 to 4 plus 8y minus y squared over 2. That's evaluated from 4 to 8. So our volume ends up being 8 pi cubic units. All right, so one more of these two integrals. We're going to find the volume of the solid. Or by revolving region, y is x squared plus 6, y equals 0, x equals 0, and x equals 2. About the y-axis again. All right, so for starters, quick rough sketch. So y equals 0, in other words, the x-axis. X is 0, in other words, the y-axis. X equals 2. And y is x squared plus 6. Vertex at 0, 6. Parabola that is opening up. And we're revolving about the y-axis. So here you can see, again, we're going to have two different behaviors. We're going to have this bottom shape spun around, but we're also going to have this outer top shape spun around to form our solid. So picture your two different types of rectangles. So let's talk about where these meet. So this vertex for our parabola is at, of course, 0, 6. And this goes out to 2. And when x is worth 2, we have an output of 10. So volume pi times. So we'll start at the bottom here. We're looking to make horizontal rectangles, so our bounds are going to be the y values, not the x values. From 0 to 6, we are out to 2. 2 squared times dy plus the integral from 6 to 10. And here we're going to need the washer method. Notice this middle chunk is missing. So the outer chunk is at an x equals 2. Outer squared minus inner squared. Well, the inner squared, if we had y is x squared plus 6, then x squared is y minus 6. X is equal to plus or minus, we'll use the plus, square root of y minus 6. So inner diameter, square root of y minus 6 squared times dy. So we have a disk method and a shell method all wrapped up into one problem there. And again, notice the bounds are y values both times. So pi times integral from 0 to 6 of 4 dy plus integral from 6 to 10 of 4 minus y plus 6 times dy. So notice I'm distributing the minus sign there. So one more little bit of cleanup and we're ready to do our integration. So volume pi times the integral from 0 to 6 of 4 dy plus the integral from 6 to 10 of 10 minus y times dy. So our volume pi times 4y evaluated from 0 to 6 plus 10y evaluated from 6 to 10 minus y squared over 2 evaluated from 6 to 10. Lots of plugging and chugging, and you should end up at 32 pi cubic units.